Modern electronics, that is the transistor, integrated circuits, and the microprocessor. Its influence is everywhere, in our homes, at the workplace, and especially in our automobiles. Today's vehicles have reached new heights of performance and sophistication. Features such as anti-lock brakes, computer-controlled fuel injection, and four-wheel active suspension are but a few of the systems challenging the skills and the knowledge of today's technicians. GM Expertech has produced this introductory series to electronics for automotive technicians worldwide. Beginning with the basic principles of electronics, this program will guide you to an understanding of automotive electronic systems, their functions, and how to diagnose them efficiently. To provide a comprehensive understanding of this subject, this video program is part of an integrated package and should be used in conjunction with this handbook. At certain points in the video program, we will ask you to stop the tape and review what you've learned by taking the appropriate self-test. These tests can be found in the back of the book. You can then evaluate your progress and follow the instructions given for your individual score. You might be asked to read a chapter in the book, review a video segment, or both. You might also be instructed to just continue with the next segment. In any case, progressing through the complete program as we suggest will give you a thorough understanding of electronics and the techniques for applying this knowledge in your profession. We will begin our study of the basic principles underlying electronics with a look at magnetism. We all know that a magnet, if suspended in air, rotates itself so that one end points to the Earth's North Pole and the other to the South Pole. The end of the magnet pointing north is called the magnet's North Pole, the other end the magnet's South Pole. A magnet is surrounded by an invisible field of force, its magnetic field. This magnetic field can be imagined as lines of force reaching from the North Pole of the magnet to its South Pole. We can visualize this force field around a magnet by sprinkling iron filings onto a glass plate which rests on a magnet. If we tap the glass lightly, the filings will align themselves in a distinct pattern around the magnet. Where the magnetic field is stronger, we see the lines of iron filings crowd together. The lines stretching from the North Pole to the South Pole indicate that there is a force of attraction running from pole to pole. This force of attraction becomes more obvious when we put two magnets close together end by end, with the South Pole facing a North Pole. The iron filings on the glass plate show that the magnetic lines of force, seeking the closest opposite force, now pass between the two magnets. We can also feel the force trying to shorten the distance between the magnets, pulling them together. The closer the magnets get to each other, the stronger the force will be. If we, however, reverse one of the two magnets so that now a North Pole faces another, the opposite happens. The magnets try to get away from each other. Thus we have demonstrated one of the fundamental laws of magnetism. Opposites attract equals repel. That is, a North Pole and a South Pole attract each other. Two South Poles, or two North Poles, will repel each other. This basic law has many applications in converting electricity into mechanical energy. This can be seen, for example, in the operation of a starter motor. Electrical energy sets up a magnetic field in the starter, which is then converted to mechanical power to crank the engine. But before we get ahead of ourselves, let us first apply the law of magnetism to the very principles of electricity. The best way to understand electricity is to examine the smallest component of an element that still retains its properties, the atom. An atom consists of a nucleus with protons and neutrons. Electrons circle around the nucleus in different orbits, much like the planets in our solar system circle the sun. The electrons on the outermost orbit are called valence electrons. To simplify matters, we are showing only the valence electrons orbiting the nuclei. In order to keep these electrons circling in their orbits, an attracting force must be exerted upon them. This force comes from the charges of the protons of the nucleus. The protons carry a positive charge, while the electrons carry a negative charge. The neutrons carry no charge, they're neutral. In keeping with the law of magnetism, the negatively charged electrons and the positive protons attract each other. The high speed with which the electrons circle around the nucleus creates a centrifugal force which prevents the electrons from colliding with the protons. The force of magnetism keeps them in their orbits. If an atom has an equal number of protons and electrons, the combined negative charge of all electrons circling a nucleus is equal to but opposite of the combined positive charge of the protons. Thus, the negative charge of the electrons and the positive charge of the protons cancel each other, and the atom has no net electrical charge. It is neutral. However, if an atom has fewer electrons than protons, the positive charge of the protons is larger than the negative charge of its electrons. Such an unbalanced atom is known as a positive ion. If an atom has more electrons than protons, the negative charge of this atom's electrons outweighs the positive charge of its protons, resulting in a negative ion. In addition to the electrons that are bound to the nuclei, there are the so-called free electrons. These free electrons can move easily in certain substances. The substances in which these free electrons can move easily are called conductors. Metals, for example, are conductors. Substances that do not permit a movement of free electrons are called insulators. Some insulators are, for example, glass, plastics, and ceramics. Free electrons can be created by disturbing the natural balance between negative electrons and positive protons in atoms. Applying a force to atoms, such as friction, heat energy, or a chemical reaction, will break a few electrons loose from their orbits, and thus create some negatively charged free electrons and an equal number of ions with a positive charge. If we then physically separate the positive ions and the free electrons through, let's say, a chemical reaction, as happens in a car battery, we have a pole where the positive ions are located and a pole where the free negatively charged electrons are located. The pole with the positive ions is the positive pole of the battery. The pole with the electrons is the negative pole. As we explained with the law of magnetism, there is a force of attraction between these two poles. The physical separation of charges, however, does not allow the electrons to rush back to the positive ions. But if we connect both poles with a conductor, thereby creating a path or circuit, the free electrons will rush to the positive ions in order to reinstate the atom's balance. It is this flow of electrons that is used in electricity. This flow of electrons through a conductor is called current. In scientific notation, the letter I is used as the symbol for current. We can measure the magnitude of current. This magnitude is expressed as the number of electrons passing a certain point in a conductor within a specified time period. The current is measured in amperes or amps. Modern electronics uses very small currents, so the current is often measured in milliamperes, abbreviated little m big A, that is, in thousandths of an ampere. Just to give you an idea of how many electrons are needed to create a small current, for a current of 1 milliampere, 6¼ million trillion electrons, that's 625 with 13 zeros after it, must pass a given point within 1 second. And once the free electrons can move through a conductor, they move extremely rapidly, at about 2/3 to 9/10 of the speed of light. The flow of electrons from a negative pole through a conductor is so powerful that the source of electrons is often referred to as providing electrical pressure. This force or pressure that is responsible for the flow of current is known as voltage or potential. The symbol for use in formulae is E. The letter E is derived from the expression electromotive force, used to describe the pressure of current. It is measured in units of volts, V. As we mentioned earlier, there are both very good conductors and materials which do not allow the flow of current. At most temperatures, all materials offer at least some resistance to the flow of current. Metals, for example, are very good conductors, offering very little resistance to the flow of current. Glass, plastic, rubber, and so on resist the flow of current very strongly. In fact, they are insulators. The phenomenon by which electron flow is resisted in a certain material is known as resistance. In many, if not all, electrical systems, we find additional resistors that will limit the amount of current flowing in the circuit. We'll come back to those later. Resistance is measured in units of ohms, represented by the capital Greek letter omega. The symbol for resistance in a formula is R. In circuit diagrams, resistors are represented by this line. To summarize, we can say that current flows through conductive materials, while it does not flow through insulators. For a current flow to occur, a source of electrical pressure or voltage is needed. Electrical current is often compared to the flow of water in a pipe. The existence of a pipe alone does not make any water flow. A source of pressure is needed, which makes the water flow. The same rule is applied to electrical current. It is not enough to have a closed loop of conducting material. We need a source of electrical pressure or voltage. In cars, this source of electrical pressure or voltage is the battery. Through chemical action, a potential difference is built up in the battery. That is, an overabundance of electrons at one terminal of the battery and a surplus of positive ions at the other. The state is called potential difference. This potential difference is the electrical pressure needed to cause a current, indicated by the letter I, to flow. The current is opposed by resistance, denoted by the letter R. In our example with the water pressure, the tap would be a resistor because it impedes the flow of water. The path that the current takes is called an electrical circuit. There are various kinds of circuits. First, let's have a look at a basic DC circuit. A basic DC circuit consists of a voltage source, here a battery, a lamp, and two connecting wires. The part which performs work in the circuit is called the load. Here the load is the lamp. In other circuits, the load can be a starter motor, a radio, power windows, and so on. If we add another load to the circuit, then we have a series circuit. A series circuit may include more than one component, a switch, a lamp, a motor, and so on. A series circuit is formed when all the current flowing through one component also flows through another. Thus, a series circuit will have one and only one path for current flow. A parallel circuit is formed when the different loads are arranged in such a manner that current can flow through one component without first having to flow through another component. A parallel circuit is therefore defined as a circuit providing two or more paths for the current flow. Many electrical circuits are a combination of series and parallel circuits. We will discuss series and parallel circuits in detail at a later point in our program. For now, let's go back to our basic electric principles. There are two theories of current flow that are applied today. One is the electron flow, where the negative electrons flow rather freely to the positive ions. This theory is what we have developed and explained so far. The other theory actually predates this one and was developed before the behavior of electrons was known. It was based on the observation of the movement of positive ions in liquids. It was noticed that in liquids, the positive ions moved from the positive pole to the negative pole. This observation led to the conventional current theory, that current moves from the positive pole to the negative pole. This theory is still the most widely accepted theory of current flow, and we will adhere to it in our program. For practical purposes, there's not much difference in the two flows. In each situation, we have a flow, the electron flow we've already mentioned. You see, every time a valence electron is removed from its orbit around a nucleus, it leaves a gap or a hole. It also leaves the atom as a positive ion, and the atom will try to attract another electron from a surrounding atom. If that happens, the hole will be filled, but another hole at the other atom from which the electron came is opened. While the electrons physically moved in one direction, the hole seems to have moved in the opposite direction. This is much like a line of people waiting to board a bus. As the first person boards, he leaves a space where he stood. The second person will move into that space, and the space will then be behind that person. As each following person moves up to fill the space in front of him, the space will actually seem to move back toward the end of the line. The whole procedure will be repeated as the next person boards the bus, and so on. Every time the people in the line move, the spaces seem to travel in the opposite direction. And if we apply this model to current flow, we will understand that when electrons flow in one direction, spaces or holes will travel in the opposite direction. As we said before, in practice, both theories of current flow are equally applicable. Since the conventional current flow theory that current is a flow from positive to negative is the one most widely applied, we will follow it too. Before we go on with the program, you should take a break and digest the materials covered so far. Then please turn to your books and do the work suggested for this part. Then follow the instructions for your next step in the training program. In electrical diagrams, symbols are used for the various components contained in a circuit, eliminating the need for drawings of these components. The symbol of a battery that we see here does not indicate any certain voltage. It simply indicates the positive and the negative sides or terminals of the battery. The same symbol is used for any power supply in a circuit. The positive side is usually symbolized by a T with a long crossbar. The T on the negative side, in contrast, has a short crossbar. This will help you identify the positive and negative terminals even in schematics that omit the positive and the negative signs. Even though the normal car battery actually consists of 6 cells, each one having a positive and a negative side, in schematics we see sometimes only one pair of terminals. The symbol used to indicate resistance can be used for different types of electrical devices which consume electrical energy, such as a light bulb, an air conditioning blower motor, and so forth. Even though the resistance of the conductors is very small and can be assumed to be zero for our purposes, it will become apparent once you start taking measurements. You'll notice slight deviations from specifications or calculations. As long as these deviations are small in proportion to the expected values, they need no further attention. Another important symbol is the ground symbol, shown here in the variations you might encounter. It represents a common return circuit to the voltage source. On negative grounded automotive systems, all grounded points are eventually connected to the negative terminal of the battery. The vehicle body provides the path. The ground symbol expresses this connection and eliminates the need for drawing this connection to the negative terminal of the battery in every schematic, as you can see here. This circuit is an example of a complete circuit without the ground symbol, whereas this schematic shows the same circuit using the ground symbol. Both circuits are identical. The second one is more economical to draw. Voltage, current, and resistance can all be measured. The work performed by an electrical current is called power. Its unit is the watt, abbreviated with a capital W. The power of a total circuit can be calculated as current times voltage. In electricity, the units can range from 1 billion to 1 trillionth. In order to avoid writing so many zeros before or behind the decimal point, Abbreviations have been established for the units of measurement. They range from giga, 1 billion, down to pico, 1 trillionth. For example, 1 megohm is 1 million ohms, simply abbreviated to 1 m omega. Kilo stands for 1,000. 20 kV thus means 20 kilovolts, or 20,000 volts. Milli stands for 1,000th. 25 millivolts, or MV, is the expression for 25 thousandths of a volt. The Greek letter U stands for micro, as in 15 UA, 15 microamperes, 15 millionths of an ampere. And the Greek letter N represents the prefix nano, 1 billionth. 10 NV is the same as 10 billionth of a volt. And finally we have the Greek letter P for pico, 1 trillionth. To measure these values, we use meters: the voltmeter, the ammeter, and the ohm meter. Today, these three meters are usually combined in one instrument, the multimeter. There are two kinds of multimeters, the analog multimeter and the digital multimeter. When using a multimeter to measure voltage potential, it is connected parallel to the circuit to be tested. This means that it's placed across a device, not in series. The units displayed are volts and millivolts. To measure current flow, we use the ammeter function of the multimeter. It's connected in series with the device, which means that the circuit being tested must be opened and the meter inserted between the two open points. This way, all the current flow is forced through the ammeter. Much like a turnstile at a baseball stadium, the ammeter keeps an exact count. The units displayed are amps and milliamps. To measure resistance, we use the ohm meter function and place the meter across the device. In this function, the multimeter is connected only to circuits that have zero battery or voltage potential. An existing circuit voltage, when applied to an ohm meter, might damage it, and will certainly cause it to give a wrong reading. Also, you must make sure that the circuit is opened to eliminate the possibility of parallel loads. Usually, the unit to be measured is disconnected from the power source. The ohm meter supplies its own power to measure resistance in units of ohms, kiloohms, and megohms. The analog multimeter uses a moving coil with a swing needle. It has a range select switch to choose function and sensitivity. The digital multimeter displays its quantities in digits on a liquid crystal display or a light-emitting diode display. When working with circuits which have a very small current flow, the meter can have a significant impact on the current in that circuit. The accuracy of the measurement might be questionable, and a low-quality meter might even damage an electronic circuit. When using the multimeter in its voltmeter function, it removes some current from the circuit in order to operate. If its internal resistance is low, it removes a significant part of the current. If the internal resistance is high, the effect on the circuit will be minimal. The higher the internal resistance of the multimeter, the less current it will draw. An older, or a very inexpensive analog meter typically has an internal resistance of 1,000 ohms per volt. A good quality analog meter has a typical internal resistance of about 20,000 ohms per volt. The highest internal resistance, and therefore the least possible effect on a circuit, is found in a high-quality digital multimeter with an internal resistance of 10 million or even more ohms per volt. The digital readout also provides a higher accuracy of the measurements than an analog meter. Furthermore, it eliminates the possibility of erroneous readings caused by looking at the scale of an analog meter from an angle. We have mentioned resistance quite often so far. It's now time that we take a closer look at resistors. Resistors are designed to provide some amount of resistance to current flow in a circuit. They can also be used to drop a voltage. This is useful when the source voltage is too high for an application. Instead of replacing the source with a lower voltage source, it's much more convenient to use a resistor. The resistor will reduce the source voltage to the desired level. Resistors do not generate any electrical energy, but simply absorb it and dissipate it in the form of heat. There are many sizes and types of resistors. They are specified by their resistance value in ohms, according to their tolerance as a percentage of the nominal value and by their power rating. The resistance values and tolerances of resistors are normally indicated by a standard color coding system. On each resistor, we find 4 colored rings. These rings are deciphered starting with the band that is closest to the end of the resistor. The first and second band tell you the first 2 digits of the ohmic value. Each color represents a different number, as you can see in this table. The third band is called the multiplier, because it indicates the number of zeros to put after the first 2 digits. The fourth colored ring indicates the tolerance. This resistor has 2 bands of red, a brown and a silver one. Looking at our conversion table, we see that red stands for 2, brown stands for 10. This means that the resistance value of this resistor is 220 ohms. The silver band indicates that there is a tolerance of 10% on either side of the nominal value. This means that this resistor can be used in applications calling for resistance values between 198 and 242 ohms. If there's no fourth band, a tolerance of 20% is indicated. In general, resistors with a 10% tolerance are suitable for average circuit use. For more critical work, such as radio circuits, resistors with a 5% tolerance would be preferred. A 5% tolerance is indicated by a gold band as the fourth band. Closer tolerances are not required except for very critical circuits. As a general rule, when you have to replace a resistor, you should always replace it with one having the same tolerance rating. Never use a resistor with a wider tolerance band, as it could cause improper operation of a circuit. Finally, we can estimate a resistor's power rating from its physical size. Physical sizes range from about 4 millimeters long by 1 millimeter diameter to about 50 millimeters long by 6 millimeters or more diameter. The former would probably have a power rating of about 1/20th of a watt, and the latter possibly 10 watts. It's important that resistors with the correct power rating or wattage are used. Wattage is the amount of heat a resistor can withstand and dissipate. Since resistors limit the flow of electricity, electrical friction causes heat to build up within the component. The resistor must be large enough to dissipate this heat to the surrounding environment without changing its own characteristic value beyond the tolerance allowed. It is usually best to operate a resistor well below its wattage rating, particularly if components are crowded on a circuit, or if there's little or no ventilation. This is another good point to stop and digest the materials covered so far. After taking a break, please turn to your books and do the work suggested for this part. Then follow the instructions for your next step in the training program.